I want to go through with you today three separate quick stories from our laboratory about ways that we might potentially improve immunogenicity of vaccines, and we're learning from live virus infections of humans and live virus vaccines in humans and animals to try and make those improvements. So we'll talk first about vaccine-induced HIV-specific CD8 positive T cells. So just by way of review, for those of you who've forgotten this bit of immunology, the class 1 system of presentation to a killer T cell is a system that we've evolved to detect intracellular infections. So if a target cell is infected by a virus, those virus products, proteins, are cleaved up into small 9 to 11 amino acid bits that are then displayed on the surface of the cell. This is recognized by a so-called killer CD8 positive T cell that then produces perforin and granzymes. Perforin pokes holes in the membrane of the T cell. Granzymes can then enter, and they cause caspase-mediated apoptotic death of the cell. So this is a very, very powerful system by which we control infections after they've bypassed, for example, the antibody response. So our laboratory, over many years, has studied this in a very algorithmic way, and to do that, we've taken people that naturally control HIV for many years without antiretroviral therapy, in some cases many decades, and they'll probably die of a non-HIV cause. And we have, in this algorithmic way, shown that their ability to control was not because of factors in the virus, it was a host factor, and it did not have to do with the frequency of their CD8 T cells, but actually it had to do with the ability of their cells to accumulate that perforin and poke holes and kill an autologous infected CD4 T cell. And that turned out to be a very critical observation. So this is about 30 years of work on a slide, but here is the real meat of the matter, is that fresh out of the blood, you can detect some minor differences between non-progressors, progressors, and progressors that are treated. But if you allow those cells to accumulate perforin by stimulating them for 5 days, now there are these very large differences with little to no overlap between patient groups. So by way of background, in 2011, we had published a paper showing that a number of HIV vaccines were not inducing very high levels of killing cells. So the first of these was a phase 2b study called the STEP study. That was a study of efficacy of CD8 T cell targeting vaccine that showed no difference in acquisition or RNA load. It was 3 doses of replication defective Ad5 vector containing 3 HIV inserts, and that targeted the CD8 T cell response. There was tremendous hope for this vaccine, and it was a real failure. And we had, at this time, no mechanism behind why we observed such little killing capacity in the cells of these individuals that were in that trial. So to go back into those samples where there are not apheresis packs and you need to work with very small numbers of cells, we needed new technologies, and we used fluorescence microscopy, where we could use small numbers of cells, and we infect cells with a RFP expressing HIV construct, and then look at the disappearance over time. So I'll run this movie, hopefully it'll run, but the left-handed movie didn't, but oh, here you go. So in red is a target cell. You can see that the gag that's labeled with RFP comes out of the cell after it's been killed, and by 2 hours, nearly all of the target cells shown in the middle have been killed, whereas there's very little change in the case of progressors. And once again, we saw this very low response in the cells of individuals that were in that STEP trial. I'm going to cut to the chase with regard to this work, and that is that what we observed is, and we went through a very similar sort of algorithmic process, is that this low ability to kill was caused not by the inability to accumulate perforin, but by the inability to degranulate or to get that perforin into the target cell. So these cells did not have sufficient antigen sensitivity to be able to do that. This is something we measure for degranulation capacity called CD107A. You can see these individuals had very low ability to degranulate to an autologous infected cell. And probably one of the first clues of what was going on here was these data that showed that pre-infection, so the individuals who were in that trial who subsequently got HIV infected, if you looked at their ability to degranulate before they were infected, that actually inversely correlated ultimately with their viral load at steady state once they did get infected. We wanted to look at other HIV vaccines and see if we saw similar things, and in fact we did. So these are the ability of the cells to accumulate perforin and granzyme B here on the left, but the ability to degranulate for 107A was very similar in between the STEP trial, the VRC's DNA followed by replication incompetent Ad5, and then a Perfectus trial with 3 DNAs followed by replication competent but attenuated VSV. It's interesting to note, though, that trial that had a replication competent vector, there's a few individuals that actually did have responses by degranulation that were quite similar to non-progressors or progressors. So I think that was probably the closest that we came to inducing such a response. Unfortunately, that vaccine has not gone to phase 3, and Perfectus has been acquired. I'm not sure the future of that vaccine regimen. This inability to granulate had to do with the sensitivity of these cells to an autologous infected CD4 positive T cell. So when you titrate out the peptides, you find that there was at least 100 to 1,000-fold difference in the ability to respond to these peptides. This was specific to HIV in that when we tested responses to SARS-CoV-2 induced by RNA vaccines or CMV responses, these differences persisted. The curves are shown here in the middle. And this was not without physiologic importance. So the area where these are the largest difference, it turns out when you run HIV-infected cells in this type of assay in parallel, that this is actually the amount of antigen of peptide MHC that's on the surface of the infected cell. It's about 3 logs below that which most people are using in a variety of different assays that are in clinical trials right now. So it is important that we ultimately mimic something closer to an HIV-infected cell in these types of assays. So this work is actually going to be published a week from Friday. So what we're saying here is that under conditions where you're using a lot of peptide, both high and low avidity cells respond, and there's no MHC downregulation caused by HIV. But when you use an HIV-infected cell, you downregulate that MHC, and there's lower occupancy, and now only the highest avidity cells respond. That defect could have been caused by many different parameters within the signaling complex, with the affinity of the TCR, the ability to activate the cell. But I'm only going to go through this very briefly. What we found was that when you titered in anti-CD3, the curves are superimposable between a vaccinee and a non-progressor. So there's no problem with the signaling cascade. But when you look at the T cell receptors of individuals that are in the STEP study, they're much more polyclonal. They were not driven to oligoclonality similar to a non-progressor. And then you take those T cell receptors and you transplant them onto normal PBMCs, the defect tracks with that. So it is, in fact, the T cell at the level of the T cell receptor. So to summarize, this vaccine-induced CD8 T cell avidity was insufficient to respond to the low level of peptide MHC on infected cells, and our assays need to more closely mimic HIV-infected cells. The poor ability to kill HIV-infected targets was attributable to TCRs, and that was a possible contributor to the recent failed efficacy trials of Ad26 vectors that failed in 2 trials called Mosaico and Imbokodo. And in addition, it's telling you that low avidity responses might benefit from further clonal selection. So driving this response further with additional immunization or more immunogenic vectors is likely the path that we should take in the future. And this, I think, offers an important benchmark for what the response should look like for killing of an HIV-infected cell. So now I'm going to switch gears to the use of VLPs to understand the induction of neutralizing antibody magnitude and durability. So our immune response has evolved not just to see exogenously administered proteins as, for example, split flu vaccines, but to see live viruses. And so we do that by a lot of different features of a live virus that all contribute to humoral and cellular response magnitude and durability. So For example, for HIV, envelope conformation is important, but also things like valency, so the number of spikes on the surface of a virus, the innate response to nucleic acids, and many of these other features. And the reason to study this is that if you know the rules, you can better engineer toward that. So spending less time on vaccines that maybe don't work, or improving vaccines that are marginal, and getting more quickly to things that actually have some chance of working. So at the beginning of this work, we decided to utilize a VLP system, so a virus-like particle, where we can change a lot of those different factors in vitro to be able to test them independently. So using this type of system, in this case, we're using Newcastle disease virus particles. It was a very immunogenic VLP that gave RSV responses in experimental animals that were at or above natural infection. So it has the ability to do that. And you can change the valency on the surface. You can change how you give it to try and imitate a live virus infection. So instead of using a bolus, for example, you can give this by a series of injections that increase in dose, keeping the total dose the same. You can encapsulate immunogenic RNAs that can stimulate TLRs, and a number of these other features. So when you do that type of experiment and you make these highly valent particles and you give it to rabbits, and you express H5 from influenza, the first shot you're into the hundreds, second shot you're into the thousands, and you get good durability. You do that with SARS-CoV-2, stabilized spike, and same story. First shot in the hundreds, second shot in the thousands for neutralizing antibodies, and you even get some breadth, even though this is a Delta plus immunization. We also see neutralizing antibodies to Omicron BA.2. So when you do that experiment with HIV, nothing happens. So even though there was a lot of hope at that time that if we had stabilized HIV, which was a tremendous advance in the field, and then expressed it similar to HPV in a highly valent particle, that now we would get much better immunogenicity, but actually that was not in fact the case. This is a very tough target for neutralizing antibodies. So we don't have time to go through all these data, but I'll just summarize them. And in the end, what we needed to do was all of the things that we had postulated were important in a live virus infection. So we needed to express it as a high valency stabilized ONV on the particle. We needed to encapsulate TLR7 and 8 agonists. We had to apply adjuvants, which gave us magnitude, but never gave us any durability. But the thing that made the biggest difference in durability was very high doses, and then an escalating dose that really imitates a live virus infection. That turned out to be a really critical thing for antibody response durability. So many different factors that imitate a live virus infection. As many things in life, everything becomes clearer in retrospect. And so when you look back, it should have been no surprise to us that dose would have been a really important factor, even in our own work. So when we give adenovirus type 4 on the GI tract, where it does not replicate as well, we see very little durability response to H5 transgene. But when we put it on the upper respiratory tree, now we get great durability in humans. This is the vaccinia vaccine. The half-life of the antibody response is measured in hundreds of years, whereas if you attenuate that virus with MVA, the response declines over months. And then hepatitis A virus, which is a non-replicating virus, it's killed. You can actually increase this half-life. Although you have this initial decline, you can increase this very substantially by increasing dose. So dose, in retrospect, is a very important parameter of live virus infections that's critical for antibody durability. So to summarize this section, durable systemic immunity can be achieved in experimental animals with VLPs if conditions simulate those of a replicating virus, and dose and escalating dose had the greatest effect on increasing the durability of the response. So lastly, the use of replicating mucosal vaccines to induce durable systemic and mucosal immunity. When we started our HIV work, we wanted to sort of play at the deep end of the pool. A lot of the early vectors and proteins that had been used were just that, and it really did not resemble a live virus at all. In retrospect, these really had very little hope of being successful. They were not conformationally correct. They were not high valency. And so using a live virus, though, puts us at this end of the immunogenicity scale. Live attenuated, of course, is not a possibility for HIV, but we can use replicating viral vectors to try and induce immunity. And these have important advantages with regard to conformation, host glycosylation, vaccine take, TLR agonists are multivalent, and you get very prolonged antigen exposure. So to mention durability of the response again, this is a challenge for many different vaccine approaches. These are the H10 and H7 mRNA from vaccines from Moderna, so this is back in 2019. Very similar decline in these antibody responses that you see following the IM administration of SARS-CoV-2 vaccines. This is the Sanofi split vaccine. You can drive these titers to H5, so these are HAI titers, to very high levels with ASO3. So similar to our rabbit studies, when you give an adjuvant, you can drive magnitude, but you don't drive durability. So by about 12 months, this is down close to the level of an unvaccinated individual. Microneut shown here also declines. But for live viruses, these antibody half-lives in the serum are measured in the decades to hundreds of years. And the reason is that the live viruses are able to drive these long-lived plasma cells, which exist in our bone marrow and crank out antibody over many, many decades, whereas some of the other more short-lived immunogens give you other types of B cells that really only produce antibodies for a relatively short period of time. And in our prior work, we had used adenovirus type 4 as a vector to deliver H5 antigens in humans. And so, as I showed you on the prior slide, we had given it on the GI tract where it was overly attenuated, but when you put it now on the upper respiratory tree, what we observed was actually quite good durability and quite respectable responses. The maturity of the B cell response continued to happen over 6 months to a year after a single intranasal dose. And so this is somatic hypermutation. It's a way that we mature or increase the affinity of our individual antibodies that are cloned here. And this continues to go on for 6 months to a year. So it's very impressive maturation. People shed this for a median of a day. And most importantly, when we brought people back at 3 to 5 years to boost them, their titers were unchanged from the peak. So this, declining antibody durability is not a feature of all vaccines. You can actually engineer potentially for profound durability in humans. I'll mention quickly that the impact of pre-existing immunity for adenovirus type 4, only because I always get asked about it, and it's not a binary thing. It's not like people that have pre-existing immunity don't get infected with a vaccine virus, but it actually is related to many different factors, including the prevalence of seropositivity, the magnitude of the vector-specific response, the immunogenicity of the transgene product. So in other words, for HIV, it might be an important problem, but for a highly immunogenic transgene, it may be like SARS-CoV-2 spike, it might be less of a problem. But when we infect even individuals who are have high levels of serum neutralizing antibodies against AD4, they still replicate the virus out to a week. They don't go out to 3 weeks, but they do replicate the virus and they do develop a response to the transgene. In terms of safety, we have not thus far seen anything above a grade 2. We see a couple of things like sore throat and cough that are specific to an intranasal administration of a vaccine platform, and a few of these other AEs, but nothing above grade 2 compared to Moderna, Pfizer mRNAs, which can give you grade 3 and grade 4. We are collaborating with the group here at Dartmouth and looking at mucosal responses to the intranasal immunization of hamsters with an AD4 that expresses SARS-CoV-2 transgene. So on the top, I'm showing you the nasal response, and on the bottom, serum. So any of the recombinants that we've made that express Wuhan, India, Brazil, they all develop serum responses, as do hamsters that are given an intramuscular injection of the J&J vaccine. But importantly, intramuscular immunization gives you nothing above background in the nose with regard to IgA, IgG, and IgM, whereas we do see these nice binding responses in nearly all the animals after intranasal inoculation. So the serum, we also, very importantly for development purposes, as well as protection of the lower respiratory tract, we do see serum antibodies after intranasal immunization. So, and those serum antibodies are at the same level in hamsters as Moderna intramuscular given mRNA. This BA.2.75 expressing AD4 is not low because it didn't work. It's all because of genetic distance. When you now look at the neutralization of BA2, it's higher, and then at the autologous BA.2.75, it's even higher. So very promising. We get serum responses, we get nasal responses in hamsters. After challenge, in this case with the Delta virus, hamsters that received AD4 Wuhan, AD4 Delta, this is a Delta challenge, there's no weight loss compared to here AD4 H5, which is our control, and the J&J AD26. So quite good protection in terms of weight loss. We're still, the replication data are still pending. So as I mentioned, we're collaborating with the group here as well as Univercells, which is, Univercells is an industrial actor that's based in Belgium, but has technology and manufacturing capacity to make biologics globally available. So they have this system of distribution where they can put small machines in country to produce vaccines. We then are collaborating with Margie Ackerman, Peter Wright, Ruth Connor, others here at Dartmouth. They have tremendous tools and ability to measure the immune response, particularly at the mucosal surfaces, and then on our experience with type 4. Just to quickly look at the product profile of something like, I'm using intranasal replicating ad as sort of an example, and here mRNA of the strength potentially of using live viruses or this type of approach. And that is that it can give you, mucosal vaccines can give you potent mucosal immunity, and they can give you quite durable protection that may last years or lifelong. Pre-existing immunity can be an issue. It's low in this particular case of a mucosally administered vaccine. These are single-dose vaccines, extremely inexpensive, great cold chain characteristics, and a single run in one of these Scalex machines from our collaborators at Exothera yields 50 to 500 million doses in 5 days. So this machine is actually maybe the size of one of the large espresso machines that you see in a restaurant. It's quite powerful. And they have even larger machines that can do 10 times that amount. So the ability to scale is quite extraordinary. All right. So I'll finish here. Effective T-cell immunity to HIV may require prolonged exposure to antigen to drive clonal selection. Durable systemic B-cell responses can be driven by replicating vectors, likely due to the total dose delivered and the persistence of that antigen. And then replicating AD4 can induce durable systemic and mucosal immunity for H5 in humans and immunity to SARS-CoV-2 in animals. These are the people that made this all possible. Stephen McGellis and Kenta Matsuda in my lab, a long list of students in our lab, NIAID collaborators, a long list of collaborators at the VRC, Fred Hutch, ICON at Mount Sinai, FDA, Division of AIDS, Mike Pansero there, Dartmouth Hitchcock, I've mentioned these folks, including Josh, and Scripps, designers of OMV, as well as Rohir and at University of Amsterdam, and then the clinical trial participants. And I'll stop there.